Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Bismillahirrahmanirrahim. Welcome back. There is another problem that we will solve it by using virtual work method. So in this problem it is given that find out the deflection at point D. So we are interested to calculate deflection at point D and we will solve it by using virtual work method. So for solving this question, first we will have to find the reaction force at point A and E. And you can see from A to B the distance is 3, from B to C the distance is 3, from C to D distance is 3, and from D to E the distance is 3. And at every section the loading will be different, and for every section the bending moment will be also different. So we will first solve it for finding the reaction force. So if I remove the reaction force at point A, so the reaction force at point A will be RA and reaction force at point E will be RE. Now you can apply the equilibrium condition that sum of all forces along y direction must be equal to 0 and upward force is taken as positive. And the second condition is that sum of all movement about any point must be equal to 0. So you can use these two equations in order to find the reaction forces at point A and E. So I will apply sum of all movement about point E is equal to 0, taking the counterclockwise as positive. So you can see at point E there are two forces which will produce movement about point E. One is this 150 kilonewton, another one is the reaction force. So starting from reaction force RA, so RA into perpendicular distance is this one. This total distance is 12. So RA into 12, and it will produce a clockwise movement. So that's why it will be negative. The second force that is producing movement about point E is 150 kilonewton. So 150 into perpendicular distance is 6. And it will be positive because it is producing a counterclockwise. So 150 kilonewton into 6 it equal to 0. So from here we can get RA will be equal to 75 kilonewton. Now by using another equation, sum of all forces along y direction must be equal to 0 and upward is positive. So you can see RA plus RE is equal to 150 kilonewton. So if you have RA, you can put the value of RA. So RE will be again equal to 75 kilonewton. Now these are the reaction forces at point A and E. Next step is that we will move toward the system, and you can see that this is a real system. So what we will do is that we will take out the section at every place, or you can take out the section between A and B, then you will have to take the section between B and C, then C and D, and D and E, and you will have to find out the moments equation. So first I will write something from this is section AB, clear, from section B to C, then C to D, and D to E. By drawing this table it will be easier for you to understand further. I will also write the boundaries condition. So our boundaries, so you can see from A to B means from 0 to 3. 0 to 3. From B to C means 3 to this point is total 6. So from 3 to 6. From C to D is from 6 to 9. 6 to 9. This is X. X start from 6 and less than or equal to 9. From D to E. So here D is 9 and E point is 12. So 9 to 12. Okay, then in next step we will find out the equation of movement for the real system as well as equation of movement for the virtual system. So we will draw it below. So what we will do is first we will section out it here. This will be section 1. Then we will section out, this will be 1, this is 2, this is 3, and this is 4. This will be section 2, then it will be section 3, and then it will be section 4. So we will section out it at 4 different places, and we will find out the moment equation for this real system. And then we will calculate the moment for the virtual system as well. So concentrate on or focus on it, so you will get. So first, when you cut out it between A and B, so it will be represented like this. So first the beam will be like this. So you can see here RA was applied and this RA was 75, and we cut the beam at a section X. So when you cut it, there will be a shear force and bending moment. This is point A, and let the cuts point is point J. Okay, so you can see the sum of all movement about point J is equal to 0 and counterclockwise is positive. So at point J there is a moment, reaction moment M, which is counterclockwise, and there due to this force 75 kilonewton, so there will be a clockwise movement. So minus 75 into X, it's equal to 0. So it means that M is equal to 75X. So this is for a the equation of movement for the real system between section A and A to B. Or you can say X is greater or equal to 0 and less or equal to 3. Now we will move toward the second section. So you can see if you section the beam over here, let me draw it, and it will give you the same equation. Now the second part is for section B to C, or X is greater or equal to 3 and less or equal to 6. So you can see there is a smaller beam and then there is a beam with the larger thickness. So if you cut the beam, so there will be a shear force and movement. And the same at point A, there is a 75 kilonewton and this distance is X. So again, this is the same scenario as the above. So its equation of movement will be, again when you solve it, it will give you moment is equal to 75X. So now we will move toward the third portion. So we will cut section. Now you can see there is a force concentrated load at point C. So we will include it. Clear? So third portion is from section C to D. From C to D. Or you can say X is greater or equal to 6 and less or equal to 9. So if you draw the free body diagram when you cut the beam at section 3. So I will draw the free body diagram over here. So it will look like this. Larger beam, then there is a, so this is point A, this is point B, and this is point, let this point is point C, and at C we have a concentrated load of 150 kilonewton, and where you cut it, there will be a shear force and bending moment M. This total distance is X. Clear? From A to B, there is 3 meter distance. From B to C is 3. So from A to C, this distance is 6 meter. There, and this remaining, this distance will be equal to X minus 6. Okay, so we will find out the moment equation for this section. So you can see, let this point is point J. So sum of all moment about point J is equal to 0, and taking the counterclockwise as positive. So you can see there are two forces. One is this 75 at point A and one is 150. They are producing moment about point J. So, and there is a reaction moment again at point J, and this will be positive because it is counterclockwise. Now this force is also producing a counterclockwise. So 150 into x minus 6, because this distance is x minus 6. This force is producing clockwise, and it will be minus 75 into perpendicular distance is x. Their sum must be equal to 0. So when you solve it, this will be equal to 75x minus 150 into x minus 6. So this is the equation of bending moment for the portion C to D. Now we will move toward the fourth section, that is section D to E. Or you can say x is greater or equal to 9 and less or equal to 12 meter. So when you cut it at this E point, so again you will see that you will get the same equation like that. Let me, if I draw it like line diagram, so this is point A, this point is point A, and at here load is 75. This is point B. For example, if this is point B, this is point C, where there is a load of 150 kilonewton is applied, and let this is point D, and this is point here, point E will be on the right side. But here if you cut the beam, so there will be a shear force and bending moment. So let this distance, total distance is x here. So this is x, and this distance is 6 meter. So definitely this distance will be x minus 6, and it is the same like this. So when you applied the moment equation, you will get the same bending moment for section D to E. So bending moment will be equal to 75x minus 150 into x minus 6. So again note them and write it in the table. I will write it. So from portion A to B, you can again check it. The bending moment equation was 75x. From B to C, it was again 75x. From C to D, it was 75x minus 150 into x minus 6. 150 into x minus 6. And from D to E, it is same, 75x minus 150 into x minus 6. Okay. I will draw a line. Okay, now I will also check you from A to, this is 75x, clear. From B to C, again it is 75x. From C to E is this one, C to D, and D to E is also this. Now we will find the moment for virtual system. So for virtual system, what we will do is that first we will apply the virtual load at point D. Why? Because we are interested to find out the deflection at point D. So I will draw it over here for virtual system. For virtual system, I will draw the line diagram. I will not draw the whole beam. So you can see there is a reaction force RA at point A. This is point A. This is point B. This is point C. This is point D. And this is point E. And reaction force at point E is RE. Okay. So for virtual method, you will apply a unit load, because here we have been asked to find out deflection, so we will apply load. If we have been asked to find the slope, so instead of load you will have to apply a unit couple. So let we apply 1 kilonewton force at point D, and for this virtual load we will calculate the reaction forces as well. Okay, so what is this total distance is 12 meter, and distance between A to B is 3 meter, B to C is 3, C to D is 3, and D to E is 3. Okay, so when you applied the equation of moment for our equilibrium condition on this in order to find the reaction force at point A and E, so when you apply it, so you will get, I will not solve it, it's a very easy. So RA will be equal to 1 over 4 times 1 over 4 kilonewton, and rest RA plus RE is equal to 1 kilonewton, so RE will be equal to 1 minus 1 over 4, which will be again equal to RE will be equal to 3 by 4 kilonewton. So this is the reaction force for this virtual load. Now what we will do is, again for section A to B, we will cut the section here. This is section 1, 1, and we will find the virtual moment. This is section 2, 2. This is section 3, 3, and this is section 4, 4. And again we will apply the we will find out the moment equation for this section. So again I will write it in front of each. So here when you draw the, there is RA, and RA is equal to 1 over 4 kilonewton. So when you cut the beam over here, there will be a shear force and a bending moment M, and let this distance is X. So you can apply sum of all moment about section 1, 1 is equal to 0, taking the counterclockwise as positive. So you can see here there is M moment, and 1 over 4 multiplied by this force is 1 over 4 kilonewton and multiplied by perpendicular distance, and it is minus because it is producing a clockwise. So minus 1 over 4 into X, which is X by 4, is equal to 0. So it means that moment will be equal to 1 X by 4. But note that this is the virtual moment, so I will write MV. So virtual moment for this section from A to B, or X is greater, I will write it for X is greater or equal to 0 and less or equal to 3. Now we will move toward the second part to cut out this section. So again, if you cut out this section and draw the free body diagram, so again you will get the same moment, because you can see the load does not change from B to C, only there is RA force, so this moment will be same. It will be again X by 4. So this is the second virtual moment for this portion. X is greater than 3 and less or equal to 6. Now we will move toward the third part, and you can see here in third part there is a force. There is no force again from C to D. There is no force in this virtual system. So again this moment, virtual moment, will be equal to X by 4 for X is greater or equal to 6 and less or equal to 9. This will be limit. Now in fourth part, you can see when you cut the beam over here, you can see there is a 1 kilonewton force. So we will draw the free body diagram for this. So you can see at point A there was 1 over 4 kilonewton. At point B there was no load. At point C there was no load. At point D there was a 1 kilonewton virtual load, and here from D to E you have cut the section, so there will be a shear force and bending moment. Clear? And this was section 4.4. So we will calculate sum of all moment about section 4.4 is equal to 0, taking the counterclockwise as positive. So let this distance where we cut the section is x. Clear? So, and this from A to point D, this distance was 9 meter, because distance between each segment is 3, so it is 9 meter. Clear? So this distance will be equal to x minus 9. So we will apply the moment equation. So you can see here there is a moment m. Due to this 1 over 4, there is a moment in clockwise, so it will be minus 1 over 4 into perpendicular distance is x, and due to this load 1 kilonewton, and it will be producing a counterclockwise, so it will be plus 1 into x minus 9. Their sum must be equal to 0. So you have this virtual moment, here I will write mv, this virtual moments will be equal to 1 over 4x into minus x minus 9, and again this virtual moment will be equal to 9 minus 3 over 4x, because when you multiply it and further simplify it, it will be 9 minus 3 over 4x. So this is the virtual moment for the segment DE. Clear? This is the virtual moment for the segment CD, C to D, and this is the virtual moment for segment B to C. I'll also write it in the table. Clear? So from A to B, the virtual moment was x by 4. It was x by 4, and again this is also x by 4. You can check below. This is again x by 4, and the last one was changed, and that was minus 9 minus 3 over 4x. One more thing that you can see, the EI value is given as I is for segment AB is 300. From B to D, it is I is 2 times than this, and I from D to E is again 300, and E is this. So EI for AB and DE will be same, but from B to C or C to D, it will be 2 times EI. So I will also write it as, because we will use it here, it is EI when you use the term. So you will put the EI here. From B to C, it will be 2 EI, because the I is double of this one. Again this will be 2 EI, and this one is again EI. Now you have completed this table, so we will further move in order to find the deflection, and we will use the same table below. Okay. So I will, instead of going to other, I will use another one so that we can switch easily. As we know that deflection is equal to integral of between two limits, and that is m into mv divided by EI into dx. So what this is general formula for between the 2 points. So deflection for AB, we can write it delta is equal to EI. Here for here it has you can see EI is same. Clear? So we will take them out. EI integral of here from A to B, the limit was 0 to 3. M for this portion is 75x, and MV is x by 4. So you can put it 75x into x by 4 into dx. Okay. You have also the limit, so it will be equal to 1 over EI, and when you integrate it, from 0 to 3 you can multiply it, it will be 75 x square over 4 into dx, and upon taking integration and putting the limits, so you will get 168.75 over EI. So this is the deflection between point A and B. For portion BC, the deflection will be equal to 1 over EI. I will go straight forward. We will put limit from 3 to 6, and since the equation is 75 and x by 4, clear, but here you can see this is 2 EI. Okay, so you have to put it 1 over 2 EI, and rest this is 75, m is 75x into mv is x by 4 into dx. So again it will be 1 over 2 EI integral of 3 to 6, and it will be 75 x square over 4 into dx is equal to, when you take the integral of this and put the limit for x, so you will get 590.625 divided by EI. When you simplify it, you will get this value. You can check it later. For portion C to D, we can also calculate, and it will be equal to 1m into mv dx over EI. So for portion C to D, you can see again this EI is 2 times EI, and the moment equation is this, and the virtual moment is this. So put the value over here. So 1 over 2 EI integral of, now limit will be from 6 to 9, and the moment equation is 75x minus 150 into x minus 6. This is moment, and mv was 1 over 4x into dx. Again this will be equal to, when you multiply and integrate it and further simplify it, so you will get 928.125. I will skip these steps because it will go lengthy and you can do it easily. Now for C to D, for D to E, deflection will be equal to, again here from D to E, this is EI only. So we will put EI only, 1 over EI integral of 9 to 12. The moment equation was same, 75x minus 150 into x minus 6, clear, and mv was changed, and mv was 9 minus 3 over 4x. 9 minus 3 over 4 into x into dx. When you multiply it and you simplify it, you will get 506.25 over EI. Now you have all the values. You can find out the deflection at point E. So the beam was like this. Again, this was point A, the reaction force. This was point B. At point C, there was a load of 150 kilonewton. At point D, there was no load in the real system. At point E, there was a reaction force at point E. So the total length was 12 meter. So this is point B, this is point C, and this is point D. So again, deflection will be like this. So in order to find out this deflection, so this deflection at point E can be found out at point D is equal to, let me tell delta 1, delta 2, delta 3 and delta 4. So you can see delta 1 plus delta 2 plus delta 3 plus delta 4. Why? Because from A to B deflection, from B to C deflection, some C to D and from D to E, it will give you deflection at point E. So you can put the value total deflection at point D is equal to delta 1. Delta 1 is given over here, which is 168.75 over EI. 168.75 over EI plus delta 2, which is 590.625 over EI plus delta 3, which is 928.125 over EI plus delta 4, which is 506.25 over EI. Now you can add them and you have the value of E and I as well, that is given over here. The value of E and I is given in the given data. E is 200 gigapascal and I is 300. Now here you will not take 600 because you have already multiplied it by 2. Clear? So you will not take I is 600. Instead you will take I is equal to 300. I will repeat here. You will put the value of I as 300 because you have already multiplied it by 2. So we have E is equal to 200 gigapascal, clear, and I is equal to 300. Let me check. 300 into 10 to the power 6 millimeter 4. So you can put the value in this equation. When you sum all this, so it will give you 2193.25 over EI. So this is deflection at point D. So deflection at point D is equal to 2193.25 divided by 200 into 10 to the power 3, and it will be here, it will be megapascal. Clear? And we will have 300 into 10 to the power 6 millimeter 4. Here, so when you solve this, so you will get 36.55 millimeter. Here, or you can see delta D is equal to 3.65 centimeter. So this is the deflection at point D. I hope you have enjoyed this video, and again I will recommend you, if you have any problem, you can see it once or 2 times, so definitely you will be able to understand it fully. By practicing it yourself, you will be able to understand any kind of problem with the help of virtual work methods. Thank you for watching my videos and keep supporting me.